Hi everyone, this video is going to be about hypothesis testing. Hypothesis testing is a really big branch of statistics, and it's really how all research statistics are conducted once you get into advanced levels of any specific field. So we're going to get right into it. This is hypothesis testing with one sample, and this is really just going to be kind of an overview on like how a hypothesis test is conducted. So first thing, a couple definitions. In statistics, a hypothesis is a claim about a property of a population. That's really just kind of like how you would maybe think of a hypothesis to be defined, or if you looked up the definition, it's pretty consistent with that definition. It's just something that maybe you think might be true, and you're going to try to find out. Just like in science or psychology, what a hypothesis would be, something that you think might be true. And a hypothesis test is a standard procedure for testing that claim and finding out, the potential validity of that claim. So let's go into a couple examples here. So the first one is a survey showed that 150 randomly selected commuters, 55% of them used cell phones while they drive. So we want to claim that most commuters use cell phones when they drive, and by most that means a majority. And 55% appears to be a majority, but you never know. That could have been, that sample by random chance just could have been over 55%. We've talked about margin of errors and such. So we want to, find out test the validity of that claim. So that is, we're going to claim that P, the population proportion, is greater than 0.5, where P is the proportion of all commuters who use cell phones when they drive. The second example, in a sample of 100 healthy adults, the mean body temperature is 98.3 degrees with a standard deviation of 0.9. We want to claim that the population mean body temperature is less than the commonly accepted value of 98.6 degrees. That is, we claim that mu is less than 98.6, where mu is the mean body temperature of all healthy adults. So here's the game plan. First, we're going to make an original assumption that the population has a given property. So for example 1, that would be that P equals 0.5. And in example 2, that is that mu equaled 98.6. And this is an important part of the hypothesis test, is making some assumption. And basically what our whole goal here is, we're going to try to disprove this assumption. That's a really important part. We're going to take this assumption. It's not so much that we're trying to prove the statistic that we found. It's more that we're trying to disprove this assumption. So we're going to make this original assumption. And then the second part is we're going to find the probability of getting the sample statistic that we got under the assumption of that first assumption that we made. So, example 1, we would find the probability of getting a p hat of 0.55 if the true population proportion really was 0.5. In example 2, we're going to find the probability of getting a sample of 98.3 if the true population mean really was 98.6. And we know it's possible because these are just samples and there's some variability in samples, but we want to find what the probability of that. If it was, a decent chance that you could get this by random chance, and we're probably going to say, well, we can't quite disprove this 98.6. But if it was highly unlikely to get this value, then maybe we can say we have some evidence to maybe disprove this original assumption. So step 3 in the game plan basically kind of states what I just said, that if the probability from part 2 is sufficiently small, so the probability is sufficiently small, given our original assumption, we have evidence to reject that original assumption and then support the proposed alternate assumption. So we would have enough evidence to reject these two assumptions and support the proposed alternate assumption, which would be, well, it wouldn't quite be this, but it would be, the alternate assumptions would be something like this and this. So that's the general idea. Don't get too caught up in the, every single particular detail right there, but that's the general idea. We want to make some assumption, or we're going to operate with some assumption and try to find the probability of getting this sample statistic. So the players here that we want to be able to express in mathematical or symbolic form, one of them is called the claim, and that is the statement that you want to support. So an example is, that the population proportion is greater than 0.5, or that the population mean is less than 98.6. And there are two key things that we need to write here and are always found in every hypothesis test. One is called the null hypothesis, and the other is called the alternate hypothesis. The null hypothesis, which we denote H sub 0, is that original assumption that we made way back up here. It's the thing that we're trying to disprove. Generally, not always, but most of the time, it's something that we're trying to disprove. And when we say, this notation right here is a very nice notation that the author used, and he says the null hypothesis, H sub 0, is, you can use a colon, that is that P equals 0.5. I wouldn't say H naught equals this, because H naught is not a value that equals anything. This is just this is what the null hypothesis is, and this is really the statement of equality of the null hypothesis. And then we have what's called the alternate hypothesis, denoted H sub 1. Also, sometimes you'll see it denoted H sub A, which is the different assumption, which is usually what we're trying to prove. So like you'll see here, H sub 1 is P is greater than 0.5, which means most people, or a majority of people. In example 2, H1 is that mu is less than 98.6. Okay, I just had a student come in, so I lost my place a little bit, but I think I was moving right down onto this page. So the next thing we just talked about null and Okay, I just had a student come in, and I just started talking into a microphone that wasn't in front of my face. I have no idea if it recorded or not. So let's pick it back up. So we talked about null and alternate hypotheses, and now let's talk about how to choose them. So the key to conducting a successful hypothesis test is to start by choosing the null and alternative hypotheses appropriately. This really is an important part, and when we do the group work in class, I'm going to that's really going to be the first step I'm going to emphasize us doing, is making sure we choose these null and alternate hypotheses correctly. So the first thing I would do is identify something called a claim. And the claim is something that you want to support, and express it symbolically. And this will help you determine what the remaining hypotheses are. One thing you need to know is that the null hypothesis, H sub 0, or also read H naught, it must impose equality. So it must say that, P equals something, or mu equals something. And again, we'll reinforce these through the group works, and you'll see these throughout the rest of this lesson. The alternate hypothesis, H1, it must be different from the null hypothesis. If possible, have it match your claim. That makes things a bit easy. So the following table demonstrates some examples. In example 1, we had a claim that most people, what did it say? It said most people, we want to claim that most commuters use cell phones when they drive. So the claim, most people use cell phones when they drive, put in symbolic terms, is that P is greater than 0.5. So, and we said that the null hypothesis must impose equality, so we're going to say for the null hypothesis that P equals 0.5. And then the alternate hypothesis must be different, and if possible, have it match your claim, which we can, because P is greater than 0.5 is different from P equals 0.5, and it does match our claim. Example 2, we want to claim that the population mean body temperature is less than the commonly accepted value of 98.6 degrees. So the claim in symbolic notation is that mu is less than 98.6 degrees. And the null hypothesis, again, we want to impose equality if possible, would be that mu equals 98.6 degrees. And then our alternate hypothesis must be different from our null hypothesis, and if possible, have it match your claim, which we can do. So we'll say that mu is less than 98.6 degrees. These are both examples of hypothesis tests called one-tailed tests right here, and there are also types of tests called two-tailed tests. And in those cases, you could have two options. You could be claiming that that some population mean equals some value, or you could say that some population mean does not equal some value, is different from some value, maybe like a commonly accepted value. And if you're trying to prove that it in fact equals some value, then again, we said the null hypothesis must impose equality. So this is that one case where you want to have the null hypothesis actually match your claim. And then your alternate hypothesis is that simply that mu does not equal 12. And if you're trying to claim that mu does not equal 12 or some value, then we'll say that the null hypothesis, again, imposes equality, so mu equals 12, and the alternate hypothesis will match our claim. A little note here by the author: if the alternate hypothesis contains a does not equal symbol, then that test we call two-tailed. Otherwise, we will call it one-tailed. So here's an example for you to try. Express each claim symbolically. So first, write a claim, just like in this row up here, and write it symbolically. And then also find your null hypothesis and your alternate hypothesis. Sometimes I write HA. It can be written as H sub 1 or H sub A. Either one are pretty accepted in the statistical world. So why don't you pause the video and go ahead and try it on your own, and then once you replay the video, then you can see if your answers match mine. Okay, so the claim here I would write as for the mean heart rate of all men is greater than 75 beats per minute. I would say that, is that mu is greater than 75. And then remember, for the alternate hypothesis, for the null hypothesis, it has to impose equality. So I would say the null hypothesis is that mu equals 75. And then for the alternate hypothesis, you can call that H sub A or H sub 1. And that would be, and that would be the same thing as your claim, which is that mu is greater than 75. Okay, cool. Let's go on to number 2. The claim is that less than 10% of Americans use public transportation. So this is a proportion here because it's percent. So we would say the claim is that P is less than 0.1 or 0.10. Then the null would be that P equals 0.10. The null always imposes equality. And the alternate hypothesis, I'll call this H1 this time. Wow, this is not working very well. Just imagine that's an H. Is that the same thing as the claim, that P is less than 0.10. All right, 3, our claim. The mean volume of fluid in all 12-ounce cloaks is 12 ounces. So that would be that the mean equals 12. Our null hypothesis has to impose equality, so it would be the same thing as our claim, that mu equals 12. And our alternate hypothesis, H sub 1, would be it has to be something different from our null hypothesis, and so it would be that mu does not equal 12 ounces. Okay. For number 4, the claim is that most people love pizza. So the way we would put that in symbolic notation is most people, that's a proportion. So that P is greater than 0.5. The null hypothesis would then be that P equals 0.5. And the alternate hypothesis would be that the same thing as the claim, that P is greater than 0.5. Okay, hope those answers matched up with what you guys got. If not, take some time to think about it and see why these would be correct. All right, so let's move on to the third page. Here are some more players in hypothesis tests. One is called the test statistic. And we're going to get more into detail into this in the next sections. For population proportions, you calculate a test statistic by this formula right here. For population means, you can either use a z-test statistic or a t-test statistic. Test statistic, that's a tough word to say really fast. Basically what these are is, you'll see kind of denoted here, is these are just z-scores or t-scores. So that's really all they are, is just z-scores or t-scores. And then what we're going to do is we're going to use those z-scores or t-scores, the test statistics, to find the probability of getting that value. Kind of like how we've been doing in Chapter 6 with normal distributions. So some more definitions here. The rejection region or the critical region is basically like the shaded region beyond that z-score or t-score. It's defined here as the set of all critical values of the test statistic that cause us to reject the null hypothesis. So it's basically the values more extreme than these z-scores or t-score. The significance level is alpha, just like how we learned it before. Alpha is just 1 minus the confidence level. And sometimes we just refer to that strictly as the significance level. And a critical value is any value on the boundary of the rejection region. Basically, it's just the value of that z-score or t value. Well, it's the value that, let me think of how to say this. It's the value of a z-score or t-score that would cut off a 0.01 or 0.05 or 0.10. Think of a critical value as like the 1.645, the 1.96, and the 2.575 that we learned about before. Those kind of z-scores that cut off the 90, 95, and 99% confidence intervals. That's basically what a critical value is. Okay, so here's an example. Using a significance level of alpha equals 0.05, find the critical z-values for each of the following hypotheses. Sketch a normal curve and the rejection region. So if your alternate hypothesis is mu is less than 98.6, which is a left-tailed test, find the critical z-value for this case. And really the key here is we're analyzing it with an alpha of 0.05. So if mu is less than 98.6, we're trying to find an alpha of basically where the area of this shaded region right here is equal to 0.05. And we're trying to find that z-score. And we've done this before, and you guys could do this again using the stuff that we learned in Chapter 6. And you look that up in a table or use software, and you're going to get that z-score, that critical value, is negative 1.645. For a mu greater than 98.6, for a right tail test, you would shade to the right of that value and find the upper 0.05. And again, you could look that up in the table, and you'd look up the bottom 0.95 in the table, and you would get positive 1.645. And if you're trying to work with an alternate hypothesis that mu does not equal 98.6, well, again, you're still working with the same alpha of 0.05, but this is what's called a two-tailed test when you have not equal. So you have to split that alpha into two parts because it's a two-tailed, so it could be either end of this distribution. So 0.05 divided by 2 is 0.025, which you see right here and here. And the z-scores that correspond to those values, we've looked them up before, is plus or minus 1.96. All right, so your turn. Try to use a significance level of alpha equals 0.01 to find the critical z-values for each of these hypotheses. So pause the video, give it a try, and then I will show you my answers. Okay, so draw the normal curve and shade the rejection region. Just because I'm short on time, I'm actually not going to do that right now. Well, actually, all right, fine. Let's just do it. Here are my curves. This software makes it a little difficult for me to mark parts in the curve. I can't like write over somewhere I've already written it once to try to move it. So trying to find where mu is less than 98.6, which is a left tail test. So we cut it off. See, what do you know? So we cut it off somewhere over here. And remember our alpha is 0.01, so we're trying to find the z-score such that this area right here is 0.01, which is a z of negative 2.33. I've got a physical table in front of me, so look that up and you see negative 2.33. For a right-tailed test, we're going to cut it off right here, which is a z of positive 2.33. And for not equal, this is going to be a two-tailed test, so we need this combined area here to be 0.01. So that means in each one, it's going to be 0.005, which corresponds to a z-score of plus or minus 2.575. Okay, cool. All right. And that whole, these examples up here about critical values, we're probably not even going to be doing those that much. What we're really going to be doing is there's a couple ways to do hypothesis tests, and one way is by looking at what's called the p-value. And that's what we're going to be, that's what I like to focus on a lot when I do my hypothesis tests and what I'm going to be focusing on in this class. So a p-value of a test statistic is the probability of getting a value of the test statistic that is at least as extreme as the one representing the sample data. So it's a measure of the test statistic, of the test statistic's extremeness, or of basically, yeah, that statistic that you got, that sample mean or sample proportion, the extremeness of that value. So let's do a couple examples. One is determine the null and alternate hypotheses for the given claim, determine whether the test is left, right, or two-tailed, and then find the p-value of the given test statistic. So I claim that p is greater than 0.25, and the sample data produces a test statistic of z equals 1.18. So this is my claim. My null is going to impose equality, so my null hypothesis is p equals 0.25. My alternate hypothesis will support my claim. And since I'm trying to claim that p is greater than 0.25, this is a right-tailed test. And I got a test statistic of 1.18. And so you would find basically just what a p-value means is basically just the probability of getting that value, which we've been doing for the last month or so now. So you're just going to look up the probability of getting a z-score greater than or equal to 1.18, and you look that up in the table. You find the probability less than that is a 0.8810, which means the probability of your region you're concerned with must be 0.119, 1 minus the 0.8810. So there you have it, and that's your p-value. Your p-value is 0.119. So basically the way to interpret that, which is important, is the probability of getting this test statistic by chance with your sample data is 0.119. So you could have just got that by chance, even if the population proportion really truly was 0.25. Okay, example 2. I claim that p does not equal 0.25, and the sample data produces a test statistic of 2.34. So my null hypothesis, again, is going to impose equality. So say that p equals 0.25. My alternate hypothesis will be the same thing as my claim, simply that p does not equal 0.25. So here, since it's not equal, I have a two-tailed test. So my p-value is going to be, remember my test statistic was this, so I would mark that on my normal curve, and it's going to be this probability of more extreme than negative, more extreme than negative 2.34 and more extreme than positive 2.34. And those two probabilities, when you look them up in the table, are 0.0096 each. So you add those two together and you get a total probability of 0.0192, and that is your p-value. And usually for p-value, I do just denote it p-value. That's pretty common notation for how to do it. Sometimes you'll just say p equals, but I like to say p-value equals. Okay? So your turn. You claim that p is less than 0.025, and the sample data produces a test statistic of z equals negative 1.85. So find the p-value of this test statistic. So pause the video, give it a try, and then resume and see if we got the same answers. All right, so the claim is that p is less than 0.25. Your null hypothesis is that p equals 0.25, and the alternate hypothesis is the same thing as your claim, that p is less than 0.25. Okay, so we'll draw our curve. We're trying to find the probability of this, something more extreme than this z-score. So that would be somewhere over here. Negative 1.85, considering that 0 is in the middle. And we're trying to find the probability that something is more extreme than that. So we would look that value up in the table, and we get, let's see, I got 0.0322. 0.0322. So that is the p-value of this test statistic. All right, so the textbook goes over these two equivalent methods of decision making. One is called the critical value method, and one is called the p-value method. I'm just going to focus on the p-value method. If you want to see the critical value method, I would say go take a look at Scott Stevens' video, at least this portion of it, and you can take a look at that. I'm just going to focus on the p-value method. And I think it's pretty straightforward, and lots of computer softwares can be really helpful to us. So here is a complete example done out. Test the following claim at the alpha equals 0.05 significance level. A survey showed that 150 randomly selected commuters, 55% have used a cell phone while they drive. We want to claim that most commuters use cell phones when they drive. So the claim is that the probability is greater than 0.5, which means most, a majority. The null hypothesis, which always imposes equality, is that p equals 0.5. And our alternate hypothesis will be the same as our claim, which is that p is greater than 0.5. So here's some information here that we have. Our p hat is 0.55, right? It's 55%, which is 0.55. Our p is 0.5. That's at least what we're saying is true in the null hypothesis. Our q is also 0.5. Remember, q is just the complement of p. And our n is 150. That's our sample size. And our alpha was given to us to be 0.05. And that's the most common alpha used in statistical studies. So is this a left, right, or two-tailed test? Well, we're trying to say that p is greater than 0.5, so that means this is a right-tailed test. Then find the test statistic. We were given this back on, let's see, page, where was it? Page 128 at the top. Here are some test statistics, and we'll get more into depth into those in the sections to follow. So you use that formula, plug in the appropriate parts into the formula, and you get a test statistic of 1.22. So then you basically have to find out, you find the critical value of z for this alpha of 0.05, and for an alpha of 0.05, a right-tailed alpha of 0.05 has a critical value of 1.645, and the test statistic of 1.22 does not fall in the rejection region. Okay, if this is our interval right here, and our rejection region is everything greater than 1.645, well, 1.22 is probably somewhere around here, so is not in the rejection region. So what we say here is that since it's not in the rejection region, the language we use here is that we cannot reject the null hypothesis. And I'll elaborate more on this language about the conclusion in a little bit. So the way that I typically do hypothesis test is by calculating the p-value of the test statistic. Instead of kind of comparing it to this critical value here. Instead, I get my test statistic, 1.22, like we did up here, and then you find the probability of getting something greater than 1.22. And you look that up in the table, and you find the probability of that is 0.1112. And the way you make your conclusion about your hypothesis test is you ask yourself if that is bigger than alpha or less than alpha. If the p-value is less than alpha, then we do something which is called rejecting the null hypothesis. If the p-value is not greater than alpha, then we do not reject the null hypothesis. So that's why here it says conclusion is that you fail to reject the null hypothesis. And then we make what's called a concluding statement. And the concluding statement here is that there is not enough data to support the claim that most commuters use cell phones when they drive. Even though our original data did show that, our sample data was 55%, which is greater than 50%, that could just be by random chance. And so we're not going to make a definitive statement and conclusion because there's not enough data to say that it certainly is. All right, and if that's the end of this example, and if you didn't quite grab everything, don't worry. This is a full example that we would do. Our goal would be to finish this example in, I forget if it's, I think it's section 8.2. We would be doing out a full example like this. So this is like a preview of what's to come. Right now it's just kind of familiarizing with the general structure of a hypothesis test. And this is really, like I said, like a full example in the next section to come. So the last thing that we really didn't talk about yet was this thing, the conclusion. And so let's talk about the phrasing of conclusions. The concluding statement is kind of this like 4 possibility scenario. And there's one that you go with more than the other, but let's break it all down. So the first thing you need to analyze is which hypothesis you wrote, of your 2 hypotheses, your null and your alternate, which one supported the claim, okay? So if your alternate hypothesis supports the claim, and this is the more often scenario, okay, but you do need to check this. So if your alternate hypothesis supports the claim, then we look to see whether we reject the null hypothesis or if we fail to reject the null hypothesis. And then by the p-value method that I talked about, we reject the null hypothesis if our p-value is smaller than alpha. And we fail to reject the null hypothesis if the p-value is greater than alpha. Okay? And then once you realize whether you reject the null hypothesis or fail to reject the null hypothesis, then you make a statement. And that statement would begin with, if you reject the null hypothesis, you said, the data supports the claim that blah, 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 whatever your claim said. And if you fail to reject the null hypothesis, you say there is not enough data to support the claim that blah, 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 whatever your claim said. Then there's a second example where you may have written a null hypothesis that supported your claim. And if your null hypothesis supported your claim and you reject the null hypothesis, remember that's if your p-value is, is smaller than alpha, then we say there is not enough data to justify rejection of the claim that blah, 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 whatever your claim was. And if you fail to reject the null hypothesis, which again, you fail to reject if your p-value is greater than alpha, then you say there is not enough data to justify rejection of the claim that such and such. So what we don't do. So if we fail to reject the null hypothesis, we did not prove it was true. And that's something important to realize in statistics. We merely did not have enough evidence to reject it. Okay? We never accept null hypotheses. Okay? Basically, we're just trying to find out whether we reject it or don't reject it. And the best analogy to this that really any I hear all the time from other statisticians and statistics teachers is this thing called the courtroom analogy. In trial, it's never the goal of the defense attorney to prove the defendant innocent, right? And the jury or the judge never proclaims or decides that a defendant is innocent, right? They either say the defendant is guilty or they say not guilty, right? You don't have to prove the defendant innocent. It's the job of the prosecution to prove the defendant is guilty. And that's kind of how we're going to treat these hypothesis tests, where the null hypothesis is kind of the defendant. You don't need to prove, there's no, proving the null hypothesis to be true is just never done. You're just trying to the end result is you either reject the null hypothesis or you don't reject the null hypothesis. And what has to happen here is the prosecution must provide sufficient evidence to reject null hypothesis. If this happens, the jury rejects and returns basically guilty, and otherwise the jury does not reject and returns a verdict of not guilty, right? Not true, just not guilty. And the jury does not return a verdict of innocent. So we never conclude that the null hypothesis is true. There are two types of errors here. I'm not really going to get into these too much. I'm not really going to get into the probability of these errors either. And the last thing I'll mention is that software can be used to find critical values and p-values. And you can go to stevenstats.com and see the demonstrations for those. And I would strongly recommend you do it. I do all of my hypothesis tests by using software and technology, so I really encourage you to, especially as some of these test statistics get really difficult to compute and get really long. And there are some that literally I've never even done by hand. So I really recommend that you start getting familiar with the calculator now. All right, so we'll reinforce these examples in class. Hope you're able to follow along for the most part, at least. If you don't get it completely, I would say don't worry about it too much. We'll reinforce it in class, ask questions when you have some, and then we're going to get into the kinds of hypothesis tests in the next two sections, which are hypothesis tests about a proportion and hypothesis tests about a mean.